Today we are going to discuss alternating current. What is alternating current? What is the peak value of alternating current? What is the instantaneous value of the alternating current? We'll also discuss what is the mean value or average value of alternating current. What is the root mean square value of alternating current? And similarly such terms there with the voltage. So that is what is the average alternating voltage? What is the root mean square voltage? What are their advantages? What is the expression for average alternating current or mean alternating current? And what is the expression for the root mean square value of alternating current? So we'll derive their expressions and we'll see that what expression and relation we get between the various terms used here. We'll also discuss AC circuits in today's discussion. That is AC through purely resistive circuit, AC through purely inductive circuit, AC through purely capacitive circuit. What is the phase relationship between instantaneous current and instantaneous voltage in all these three cases there. We'll also discuss what is inductive reactance, what is capacitive reactance there, and what will be the plot of these inductive reactance and capacitive reactance with frequency. So all these we'll discuss in today's discussion. Along with that, we'll also discuss one small tip there with which you can remember the phase relationship between instantaneous current and voltage in any AC circuit, whether it is your capacitive circuit or inductive circuit there. So all these we'll discuss in today's discussion. So let's start alternating current. Alternating current is one which changes its magnitude and direction periodically with time. Whereas the direct current was there, which is flowing in one direction. Of course, direct current in a strict sense is one which is not changing its magnitude or its direction. So it is moving with constant magnitude and in a particular direction. But direct current is normally a current which is flowing in only one direction there. So it may be there that the current is changing its magnitude, but as long as it is not changing its direction, it is the direct current. Like you can have direct current there. If suppose the current is here and this is the time, if it is a direct current in a strict sense, in that case it has same magnitude, it is flowing in one direction only. But you can have also the current which is flowing like this. This is also flowing only in one direction. Of course, the magnitude is not constant, it is changing with time. So this is also direct current. But if you consider the alternating one, in that case, it is this particular representation for alternating current. That means this is the current, this is suppose the time there. So its magnitude is different at different instant. Also, after a particular interval of time, say half time period, it is changing its direction also. So it is flowing in one direction as well as in the other direction. That is why we say that alternating current is the one which is changing its magnitude and direction periodically with time. We can represent this current as I equals to I naught sine omega t. Now, since we have said that alternating current is one which is changing its magnitude and direction periodically with time, it means at different instant of time it will have the different value. So that is why this I is the current which is called as the instantaneous current. It will give you the value of the current at that particular instant of time. So this is the instantaneous current. Whereas this I naught will represent the peak value of current. Like here, you see this is the peak value. So this is your I naught. Similarly, in the other direction also, we can show that this is your minus I naught there. So this is the peak value and I is the instantaneous value of the current. Two terms we define in this alternating current. One is the average alternating current and another is the root mean square alternating current. So first let's take average alternating current or mean alternating current. This is the constant value of current, or you can say this is the constant direct current, which will send same amount of charge in same duration of time as supplied by alternating current in its half cycle. So this is the constant current which supplies same magnitude of charge or same amount of charge in same duration of time as supplied by alternating current in its half cycle. So suppose we want to find its expression. In that case, let's assume that let I equals to I naught sine omega t be instantaneous current. So here I we can write it as your dq by dt, or dq will be your I dt. And what is this dq? dq, we can assume that it is the small amount of charge which has flown through the circuit in time dt. So this is a small amount of charge that has passed through the circuit in time dt. So now if you take the total charge supplied in half cycle, this will be integral of this dq. So we can write for I, we can write it as your I naught sine omega t dt, and is integrated from 0 to t by 2, because we are taking it for half cycle. So in that case, it is your I naught integral of this sine omega t dt, that will be your minus cos omega t by omega. So in that case, this limit is there, 0 to t by 2. So this is your minus I naught by omega cos 2 pi by t into 2 t by 2, because the omega we can write it as 2 pi by t, and it is 0. So this is now minus I naught by omega. This is your cos pi, which is minus 1. Cos 0 is 1. So in that case, it is your 2 I naught by omega. This is suppose your first equation. Now let I average be mean alternating current. So in that case, by definition, what we can write? It will supply the same amount of charge in the same duration of time, that is the half cycle. So it is Q will be equals to I average into T by 2. This is your second equation. Now if you equate equation 1 and 2, because both are equal to Q, so in that case, from equation 1 and 2, what we get? I average into T by 2. This is your 2 I naught by pi, 2 I naught by omega. And what we can write for this? I average T by 2, 2 I naught by omega, it is your 2 pi by t. So this t, if you take it, it will come on the numerator, that is 2 I naught by t divided by 2 pi. So now you can see t will get cancelled, 2 will get cancelled, and what will get for I average? This is your 2 I naught by pi. This is the expression for the average current. That was the expression for average current, and that we have taken as 2 I naught by pi. There we have taken it for half cycle. Why not we define average current for one full cycle? The reason is that if you take full cycle, in that case, if you consider that the charge which is supplied in half cycle in one direction, that is, suppose this is the area enclosed, so that I and T graph there will give you the charge supplied in half cycle. Obviously, in the next half, it will be the same magnitude. So, but it will be flowing in opposite direction. So the net charge which is supplied in one full cycle will be 0. So if the net charge is 0, in that case, what will be the value of the average value? Average current in one full cycle, this will be 0 because the net charge is 0 there in one full cycle or in one complete cycle there. In that case, the average value will also be 0. That you can check it in this mathematically also. Q was your integral dq. So this is your I naught sine omega t dt, integral from 0 to t. We are taking it for one full cycle there. So this is equals to your I naught and then it is your minus cos omega t by omega 0 to t. So it is your minus I naught by omega cos. It is 2 pi by t into t minus cos 0. And that is your I naught by omega. And it is now cos 2 pi. That value is 1. Cos 0 is also 1. So it is your 1 minus 1. That is 0. So the net charge supplied in one complete cycle is 0. So I average will be also 0. Because how you are getting that? I average into t. This is your 0, that is your Q. So I average will be equals to 0. So this is how you can show that average current over one complete cycle is 0. This is the reason why we are not defining average current there for one full cycle. We are defining in terms of the half cycle. If at all you want to define it for one full cycle, then you have to take that it is the constant current which supplies same magnitude of the charge in same duration of time as supplied by alternating current in one full cycle. That is the magnitude of the charge, not the net charge. So in that case, you will calculate what is the charge supplied in half cycle, what is the charge supplied in the other half cycle, and you will take the magnitude, not the net value of the charge. So in that case, you can get the same expression what we have got it earlier for average alternating current. Let's now take root mean square value of alternating current or RMS current there. It is the constant current which produces same amount of heat in same duration of time as produced by alternating current in same resistor in one full cycle. Suppose you have a resistor and its resistances are. Whatever heat is produced by alternating current in one full cycle, it is the same amount of heat will be produced by a constant current in same duration of time. That constant current we call it as the root mean square current. So this is how we define root mean square value of current or RMS value of the current. It is the constant current which produces same amount of heat in a given resistor in same duration of time as produced by alternating current in one complete cycle. So suppose if you want to derive the expression for this one, so let I equals to I naught sine omega t be instantaneous current through a resistor R, and delta H be heat developed in it in time dt. So what we can write for dH, this is your I square R dt, and this can be written as your I naught sine omega t whole square R dt. So this is your dH. Total heat developed in one full cycle, if I represent it by H, then this will be integral of this dH, which is your I naught square sine square omega t R dt integral from 0 to capital T. Now this we can write it as your I naught square R Suppose I multiply by 2 and divide also by 2. So that this particular expression, it is in the form of 1 minus cos. This will be in the form 1 minus cos 2 omega t dt. This term will be there. It is integral 0 to t. 2 sin square omega t, we have written it as your 1 minus cos 2 omega t, because the cos 2 theta is your cos square theta minus sin square theta. That can be written as your 1 minus 2 sin square theta. So that if you consider 2 sin square theta, it will be how much? It will be equals to 1 minus cos 2 theta. So that is what we have used here. Now this time if you integrate, it is your I naught square r by 2. Integral dt will be your t. Then cos 2 omega t integral will be your, this is your sine 2 omega t by 2 omega, and limit is from 0 to capital T. So this is equals to your I naught square r by 2. This is t minus 0 minus 1 by 2 omega sine 2 into 2 pi by d into t minus sine 0. And now if you substitute I naught square r by 2 into t minus this term, it is your sine 4 pi, it is sine 0, so it is your 1 minus 1, and that is your 0. So this is ultimately your I naught square r t divided by 2. Suppose I call it as equation number 1. Now let I RMS be root mean square value of the current. So it is your root mean square current. Therefore, by definition, H will be equals to I RMS whole square R into T, because it will be producing the same amount of heat in same duration of time. Time was 1 full cycle, so we have taken T there. So it is the same heat. So now from equation 1 and 2, if you compare, then what will get? I RMS whole square RT. This is your I naught square RT by 2. And that gives that I RMS is equals to I naught by root 2. So this is the expression for root mean square value of alternating current. So just to sum up, we have got the expression for I average as 2 I naught by pi. I RMS, we have got it as your I naught by root 2. So you can get the relation between I average or I RMS in terms of your I naught or in terms of one another. The way we have defined for alternating current, that is the average current or average alternating current, root mean square value of the current or RMS value of the current, same way we can define it for the voltage also. Like if it is their instantaneous voltage, so that we can write it as your E equals to E naught sine omega t. This is the alternating voltage. So this is your E equals to E naught sine omega t. E naught is the instantaneous value. E is the instantaneous value. E naught is the peak value of the voltage there. Similarly, if suppose you have to define average alternating voltage, so we can say that it is the constant voltage which will supply same amount of charge in same duration of time as supplied by alternating voltage in half cycle. So same way derivation will be there, and there you will get the expression for E average as your 2 E naught by pi. Similarly, if you have to define RMS voltage, in that case we can say that it is the constant voltage which produces same amount of heat in a given resistor in same duration of time as produced by alternating voltage in one full cycle. So there also, if you derive, you will get the expression for E RMS as E naught by root 2. So this is how you can get it, because you know that for I which we have taken, if it is I, it was your dq by dt. So we can write dq as I dt. For voltage, in terms of the voltage, if I have to represent this one, in that case, what it will be? It will be your E by R, where R will be the resistance there of the circuit. This is your dq. Now you just integrate, and for this E, we can write it as your E naught sine omega t dt there, divided by R. This is your dq. So if you have to find q, it is the integral of this from 0 to t by 2. Exactly same way you will proceed. Only thing it will be there. Now in place of I naught, it is your E naught, and one additional term in the denominator is there, that is the resistance. So similar will be there for this RMS one. There also R term will be there, resistance term. When you are comparing the both sides, that is equation 1 and 2, that term will get cancelled, and you will ultimately get the same expression. So using the derivation of average alternating current or RMS alternating current, you can derive for the voltage also. Let's now take AC circuits. Now in this one, we will take AC through a purely resistive circuit, AC through purely inductive circuit, AC through purely capacitive circuit. Let's first take AC through a purely resistive circuit. That means we have an AC source and we connect it to a resistor. So suppose R is the resistance of this external resistance, E is the instantaneous voltage, and I is the instantaneous current. So if I assume that let E equals to E naught sine omega t be instantaneous voltage and I be instantaneous current, then by circuit equation, what we can write? E minus Ri, this is 0. E is the voltage here, and the voltage across the resistor, this will be equals to Ri. If you are using Kirchhoff's rules there, in that case it will be just in opposite direction there. That means if the voltage is here positive, this will be negative there. So that the net voltage of the circuit is 0, as it is a closed circuit. So in that case, this is equals to Ri is E, or E was your E naught sine omega t. So I can be written as your E naught by R sine omega t. Now you see this E naught by R. This is a current term. Dimensionally it will be current, voltage by resistance. So this we can represent as I naught, which will represent the peak value of the current there. Suppose I call this as equation number 1 and this as equation number 2. So E equals to E naught sine omega t gives the instantaneous voltage, and I is equals to I naught sine omega t gives the instantaneous current. Now if you look at their phase, here it is your sine omega t and it is the omega t term there. Here also it is your sine omega t. So that means instantaneous current and voltage in purely resistive circuit, they are in the same phase. So both are there in the same phase. So that is the conclusion what we can get from this AC circuit there, that both are in the same phase. If suppose you are representing in a phasor diagram, that means we represent the phase relationship there. So if I consider that this is the direction in which we have the voltage across the resistor, current is also in the same direction, so we'll represent it as your I. That means both are in the same phase. And if you are representing in this terms of the sinusoidal curve there, in that case both will have the same nature there, because both are in the same phase. The peak value will differ depending upon what is the resistance of the circuit there. Let's now take AC through a purely capacitive circuit. Here we have the AC source. It is connected to a capacitor of capacitance C. Again, if I assume that E equals to E naught sine omega t is the instantaneous voltage and I is the instantaneous current in the circuit, suppose we assume that Q is the charge on the capacitor at that particular moment. So by circuit equation, what we can write? This voltage E minus Q by C, because Q by C will give you the voltage across the capacitor. This is 0, or Q is equals by C is equals to E, or Q is equals to C into E naught sine omega t. Because for E we can put E naught sine omega t. Now if you differentiate it, differentiating with respect to t, we'll get dq by dt. This is C. E naught, differential of sine will be your cos omega t into omega, or I will be equals to omega C E naught cos omega t. This is the expression for the instantaneous current. We can just try to slightly arrange or modify this expression. We can write this one as I equals to E naught by 1 by omega C. This omega C in the numerator we have taken in the denominator of denominator. And this is cos omega t. We can write this one as sine omega t plus pi by 2, because sine 90 plus theta is your cos theta. So this is E naught. Now this term 1 by omega c, we represent it as xc. And this is your sine omega t plus pi by 2. This xc is called capacitive reactance. This will be a term which will indicate what is the opposition offered to alternating current by the capacitor. That means this is similar to the term of the resistance there. Role is similar. So here, and dimensionally also if you take, this is the term which is coming in place of the resistance there, as it is the voltage, and dimensionally it should represent current term there, because on left side we have the current term here. So this is called as the capacitive reactance, and the value of this one is your 1 by omega c. Second thing, if this was your equation 1, and suppose I call this as equation number 2, or let it be this expression, final one, I equals to I naught. This term will be written as your I naught. So this is your I naught sine omega t plus pi by 2. This is your third equation, second equation. This is your second equation. Now here for I naught we have just taken E naught by xc. So now if you compare equation 1 and equation 2, this time the instantaneous voltage and current, they do not have the same phase. Here it is your omega t, it is your omega t plus pi by 2. So what we can conclude from this, in purely capacitive circuit, instantaneous current will be pi by 2 ahead of instantaneous voltage. So current will be leading voltage by pi by 2 in purely capacitive circuit. So if you have to represent that one in graph there, or in the, if you have to represent this in phasor diagram, then in that case, suppose we take the current and voltage there. So if it is your capacitive circuit, current, suppose if I represent along x-axis, it has to be 90 degree ahead of voltage. So that means this one will be representing the voltage across capacitor. So this one will represent your VC. So in phasor diagram, if you are representing, in that case, this is giving you VC. That means this is the current and this is your voltage across capacitor, which is 90 degree behind this current. Xc as 1 by omega c. If you consider that it is for DC, so for DC, what will be the value of this Xc? This we can also write it as your 1 by 2 pi Fc. For DC, F is 0, frequency will be 0 because the time period is infinite. Okay. For DC, it is infinity. So Xc value will be how much? It will be 1 by 0, or this is infinite. So that means a capacitor will block DC. This is the reason why you might have noticed, if you are solving any numerical there in electricity, in the network, there are some resistances and some capacitors are also shown in some branches there. In that case, all those branches where the capacitors are there, we treat them as open circuit. That means we just assume that there is no current flowing in that particular branch once the circuit has acquired a steady state. And why we are taking that? Because you can see that the resistance offered by the capacitor in steady state to DC will be infinite. So no current will flow through that part. Let's take a case of purely inductive circuit, AC through a purely inductive circuit. So this time again we have the AC source connected to an inductor of inductance L. So if I is the instantaneous current, suppose I assume that let I equals to I naught sine omega t be instantaneous current, E be instantaneous voltage in the inductive circuit of inductance L. So by circuit equation, what we can get? E minus L di by dt, because L di by dt will be the voltage across the inductor there. This term should be 0, or E is equals to L d upon dt. For I we can write I naught sine omega t, and this is written as your L. This is your I naught, differential will be your cos omega t into omega. That means it is your omega L I naught cos omega t. So E is equals to I naught omega L, and cos omega t we can write it as sine omega t plus pi by 2. Because sine 90 plus theta is your cos theta. Again, this term omega L, this is the current, this is the voltage. Obviously, it must be coming in place of dimensionally resistance term there. So this is written as XL sine omega t plus pi by 2. Now again, if you consider here, this we can write it as your E naught sine omega t plus pi by 2. Of course, here we have taken XL, and this is called as the inductive reactance. This is the inductive reactance. XC was the capacitive reactance. This is the inductive reactance, and this is your omega L. So that can be written also as your 2 pi F into L. So here, if you consider now that for DC, F is 0, so XL will be 0. That means an ideal inductor will not offer any opposition to the flow of DC. So this is your XL being 0. And now if you compare from equation 1 and 2, so in that case we find that in purely inductive circuit, instantaneous voltage will be leading instantaneous current by pi by 2. So there will be a phase difference between the two, instantaneous voltage and current, and the voltage will be leading current by pi by 2. Again, if you show this phasor relation or phasor diagram there in that case, if we show on x-axis current there, that means this is the direction current is there, and as the voltage is 90 degree ahead, so in that case voltage across inductor I will show along positive z direction there, so that it has a phase difference of 90 degree between the two. So this is the phasor representation for voltage and current there. Sometimes you may be asked to plot a graph of inductive reactance and capacitive reactance with frequency. So if you have to plot the graph of inductive reactance with frequency, we know that inductive reactance is your omega L, XL is omega L, that means it is 2 pi F into L. So we can show that XL is proportional to F, directly proportional. So in that case its graph will be, if this is F, this is your XL, in that case it will be a straight line. But if you consider the graph between capacitive reactance and frequency, so capacitive reactance XC is your 1 by omega C, which is 1 by 2 pi F into C. So from here we get that XC is inversely proportional to F. So if you plot its graph, in that case we have here XC and this is frequency. So the graph will be like this. Here we can show that XL is directly proportional to F. Here XC is inversely proportional to F. So this is the plot of inductive reactance, capacitive reactance with frequency. If we just sum up the phase relationship, in that case we find that in purely resistive circuit, instantaneous current and voltage are in same phase. In purely capacitive circuit, instantaneous current leads voltage by pi by 2. In purely inductive circuit, instantaneous voltage leads instantaneous current by pi by 2. Sometimes you may get questions based on that, their phase relation, or in solving the numerical also you can use them. Just to remember this, you remember just one word, that is civil. Here, how we are using it, suppose we take the first three letters. This is your CIV. This C we are using for capacitive circuit. So here you can see now it is I coming first and then it is your V. So what we can remember, that in capacitive circuit instantaneous current will lead instantaneous voltage by pi by 2. Similarly, if you take the last three, it is VIL. This L we are using for inductive circuit. So again now you can see, now this time V is coming first and then it is I. So in inductive circuit, instantaneous voltage will lead instantaneous current by pi by 2. So if you just remember this word, you can easily remember or recall the phase relationship between instantaneous current and instantaneous voltage there.